Oh boy.
Does everyone who wants the written SOP have one or have a way to access it?
Why don't you send it to everyone after the meeting? Okay,
Yeah,
the recording has started. We're going to be discussing today processing of headwall hyperspectral imagery. Eric Deutsch has worked with us here at USDA Sustainable Ag Lab and Hydrology Remote Sensing Lab over the past summer, processing imagery that was collected by Matt and Paul Adler in April of 2020 down here at BARC. And this is the kind of final report and training from Eric. So Eric, take it away.
Yeah, sure. Thanks for that introduction. This upcoming training will be heavily following the SOP that I have created and is approaching its final form. I need to create one or two additional comments, but other than that, this SOP is in a pretty final state. And this has been distributed to a lot of people, but I can also distribute it in the future, or someone else who already has it can distribute it if that's needed. I'm going to be more or less following this, but I will be keeping it on a second screen just as sort of a cheat sheet. So to process the imagery, overall, we need 3 pieces of software. The first is SpectralView, provided by Headwall. The second is ImageJ, which you can see on my taskbar down here. And the third is a piece of GIS software, and I would recommend QGIS. To quickly go over how you acquire these software, for SpectralView, I recommend it's a very painless process to directly contact Headwall. And if you search just this and you go to this link, you can click it, input your information, select topic. You could just do license request and then write the serial number of your sensor here. You don't need to submit anything for here. Just do like software acquisition or license request in the summary, type whatever additional info, and then submit it. They'll get back to you very quickly, which is what I've noticed, typically less than 2 days. This first ticket where you express an interest in acquiring the software, they'll give you the software, but you won't have the license for it. So you won't be able to actually process data. What you need to do to get a license is enter SpectralView, and it will look like this, except open will be grayed out too, just like these 3 other options. You go to File, License Request, and it'll generate a file that you'll give to Headwall, and the file can be named whatever you want. Once you generate that file, just ignore this. This is actually out of date. You will create a second ticket, or you will respond to the existing ticket that you've made in which you received the software, saying, okay, here's the license file, and then they'll get back to you with the actual, with a file that you put within the, hold on, they'll give you a file and they'll just say, place it in the following directory. And oftentimes that directory will be in your C drive under Headwall, and then it'll be somewhere here. I don't quite remember where, but they'll let you know. So that's that. The next piece of software that you want is QGIS. It's a major piece of geospatial software. It's very easy to download. You just go to download and you can do standalone, or if you have a different operating system, you can go to one of these. ImageJ is the final piece of software. It's quite a bit more niche, but you could just search ImageJ, and then you could download it from here for any operating system that you're using. Now, let's go from data acquisition I don't know what everyone's standard protocol is, but for my sake, for my data, we have a box server from which we can download data. This is one such image data repository. And for your images, you can just right-click on the folder, download. You can X out of that, and then it'll do some processing, and then it'll start downloading. And I'm just going to cancel that right now. Just as a heads up, I've noticed that sometimes it doesn't download all of the folders and all of the subfolders. So if at some point you seem to be missing files, or your flight mission, when you like mow the lawn with the drone, it seems to exclude some tiles, or something's just up, something's just weird, I would first suggest that you check the where the location where you downloaded it from, to see if you're actually missing data, stuff that wasn't downloaded. But let's just pretend that we downloaded data, and we are now going to begin the processing steps. I've prepared a set of training data, and this is based on some existing data that we had. It's just a subset, so we only have we have fewer files. Yeah, just to help with processing time during this tutorial. This you don't have to worry about just yet, but when you at least download it with the data management system that I've experienced, within a given flight path, you'll have a dark ref folder. This just holds the dark reference, and you'll have the folder that has all of the files that you need to process data. Okay, so let's just continue. So the first thing that we want to do is find the folder. Sorry, these are semi-processed folders, so I forgot to reset them for this training. But what we want to do is go into this folder that has all of the header files and images. And I suggest changing your view to details, and then you sort by type, and then you go to the PNG files. And originally it'll look like this. So it'll be raw and then a number, and these numbers are indicative of the order in which these tiles were taken. The lower the number, the earlier in the flight they were taken. And the first thing that we want to do is look at all of these pictures and find the one or the ones that have a tarp in it. And you'll be able to see, because the image will be much darker because it's going to be saturated by the tarp. And we want to keep a note of what this number is. So 9472. Let's go back into Headwall, and we're going to open that file. And first off, let me just quickly, I'm just, so it looks more like what we actually see when you first download the data. These are some processed images, so I just deleted them. And when we open the file, it'll look like this, except for scene white reference. So we just know 9472 is the file that has the tarp. So double click it, go to select, so that selects all of the bands. If you want to just select RGB, which you don't want to do at this step, you have to clear out the existing check marks and then do select RGB. And you could see that it already selected one. But let's do all, so we could see 270 bands selected. We can just go to open now. So now it's beginning to render, and we have the image. And if we click on this chart icon, spectral plot, and we hover over it, the y-axis will have counts. So digital number, basically. And that's good for what we want at the moment. Next, we want to go to radiance. So we click radiance here, and we need to select the dark reference. And that's easy. So we just go to the folder that has the flight mission that we're actually working with. So in my case, for training, airport 3 centimeters, and then dark ref, and it's just this one. That should be the only folder in that file that you can select. And we'll do select key, create cube. So this will, some of these processing steps will take a moment, and that's okay. Once the cube is all done, we do open, select all, and then open again. So now it generated a second image. We can now X out of that. If we look at the spectral plot button again and hover over, now it's in units of radians, which is perfect. Now that we have that, let's just process all of the image tiles that we have to radians. And to do that, you go to the batch tool, and this is going to be a very worthwhile menu and like sub menus to navigate. Otherwise, you'll have to do them all individually, and that's not going to be fun. But let's go to Radiance batch. And now it gives us an option to import the files. So you want to actually push this button on the far right, and let's navigate to the original folder that has the tiles. And now we see all of these tiles that are just the number.header we want to select. And it doesn't really matter if we selected the radiance file that we just generated, because we could always just overwrite that data. Hold on one second. Maybe that is important. Let's just do that. So you can just, what you can do is you could click the top one, hold shift, click the bottom, and then hold control and click files that you want to exclude. So now we have 6 entries, which is what I expect. We have all of the files selected, all of the bands selected. Now we just have to select the dark reference once again. Now it's going to create a suffix. It did it for the first one that we made, but this is just going to be at the end of the file names. You could just overwrite it. So like the one we just generated, it'll just overwrite it with the same data, and that's totally fine. So yeah, this is one of the longer processing steps just because it's doing a lot of processing. In the meantime, let me see if there's anything worth going over. A piece of software that I highly suggest that you use for organization is Microsoft Excel. While this is processing in the background, I am just going to show you one such organization schema that I've developed. And it could be useful for keeping track of your level of processing for different flight missions. If it chooses to open, that is. There we go. So this is something that I have. In one field, in like the first sheet is all of the fields that we are due to process. The status, and the status is informed by this key. So stuff that I haven't yet started, stuff that I've processed to reflectance, but I haven't orthorectified, stuff that was reviewed but was deemed maybe that it should be reworked or improved, pending review. Once something is approved, data processing. So now this is the step where I process everything with all of their bands, and then completed, it's completely done and discarded. And I will return to that because this is almost done, and I'll show you what organization method I use on a per field basis. as opposed to this overall status update. So we're now done everything. All the tiles are in radiance and with all of their bands. So we can now X out of that. And now we can go to reflectance. Well, actually what we want to do is now open the field that has the TARP that's now in radiance, which you can see by the RD suffix. We'll select all of the bands, open. Let's just verify that everything processed correctly. It did because radiance is in the y-axis. And now we want to give the software the information that it needs to go from radiance to reflectance. And to do that, we now need to go to the TARP. We'll zoom in on the TARP. You can hold Control and zoom in with your mouse wheel. And we want to right-click on a pixel on the white section of the TARP that doesn't have any creases or folds or dirt on it. So something like this is a no-go. But if we just go like right here, right-click and do classify, it's going to generate this new window. And what we want to do, you could see some of these boundaries that it automatically drew for the extent of the box. We want to just draw it around roughly the white section. It doesn't really need to be completely only encompassing the white section, as in only containing it. But this is going to be used to just train like whatever algorithm it's using to generate reflectance. And we can do calculate, and it's trying to only put green pixels over the white section of the TARP. And you can modify how picky it is by changing the SAM limit. And I suggest starting at 0.03 and then do recalculate. And you want to lower it until it gets to about 500 to 700 seed pixels. And it'll very quickly go to 1 or 0. Like if I just lower it by that again, now we're at 1. But we know it's between that. So let's do 2.7. Okay, we're getting closer. 2.6. Let's do 2.55. Okay, so that's good enough. 0.0258. And if we look in this, it seems reasonable that it's only containing white, that the green is only over white pixels, and we'll do test calculated. And that looks about right. And what we want to do now is go up here to save, calculate it as white reference. And it's important to ensure that the reflectance profile that you're using, you have 3 options. It's the 56%. 11 corresponds to black, 32 to gray, and then 56% to white. And we will just hit OK. So with this classifying data now completed, we can actually just go straight to batch and then reflectance batch. And we can add the files. Now, when you have many more tiles than this, it can be very difficult or annoying to go between, like just to highlight the ones you want. You could search for something to help you isolate the tiles that you want. So in my case, I'm going to search for _rd.hdr. So now it only pops up the radiance files, which is what we want. So now the white reference should automatically be populated here. If it isn't, for any weird reason, it will be in the same folder where the imagery tiles and header tiles, the header files for them will be, and it'll be named scene white reference. So that should be input here. Batch, it's now going to add the suffix _rf, and we'll just start that process. So now we'll see, you could see in real time, these are now being added or generated in the same file directory. And that's going to be true for any product that's generated from SpectralView, at least for this SOP. Mm. Okay, so now is when things begin to get a little more complicated, and this is where we begin the orthorectification process, because now all we did was convert the pixels basically from digital number to reflectance, but on the ground, like they still on the ground, they're all going to be distorted and wavy just because it, like turbulence and whatnot, hasn't been accounted for. So now we're going to begin the orthorectification process. And to do so, let's open the reflectance file that's associated with the tile that has the calibration tarp. And this time, instead of doing all bands, we're actually just going to do RGB, because the process of orthorectification is done over many iterations, and you don't want to constantly reprocess all of the bands. So we're just going to do the red, green, and blue band, which you can see here. And now we are going to do the first step of orthorectification, which is actually just going to be making sure that the aspect ratio is correct. And by doing that, we're going to be turning this rectangular tarp, or at least in appearance, square, which is what it actually is. It's a 3 by 3 meter tarp. So we need to squish the imagery in such a way that it becomes square. And to do that, we will go to the orthorectification button, and the values that you see here will generally be provided by Headwall, and we are expected to modify them slightly given certain flight conditions and whatnot. So what we want to do is start with 0 for the altitude offset. That's just our baseline. And we are going to ensure that save longitude and latitude into IGM file is not checked. And we are going to check, at least if you're using like a Planix GPS, in a Planix GPS unit, click GeoID correction, ensure that invert columns is correct, and then save to ortho INI locally. And we are going to process this image just as is. And now it's going to put us into a preview. And what we want to do before we utilize external software is just eyeball the tarp and see if it approximates a square. In this case, I think that we can improve on it. It looks a little more rectangular than square. So we don't know which way we need to change the altitude offset to make it do what we want. So just choose a random number, and I'm going to choose -5. Why not? And we'll do it again. And this is going to stretch the image in one way. So now it looks wider than it is tall. And if we, let's say, do -15, it should now look a lot wider than it is tall. And that's what we see. So we know if we want to try to even this out, we actually need to go in the other direction. So let's try 10. And then start orthorectification. So now it's taller than it is wide, which isn't bad because now it's behaving as we'd expect it to. We'll try, in this case, just to save some time, Let's just try 7. Try to keep having, and we'll get to something approximate pretty quickly. So yeah, let's just say that this looks good enough for just our rough eyeball overview. And we now need external software to be more precise with our measurements of squareness. So what we want to do is ensure that we could clear it, select RGB, but that's already there by default. We'll create cube, open, select, open, and now it produces this image. And what we want to do is click on the camera button. That's going to take a PNG file, which is just like an image file. And we are going to use this in another piece of software to actually measure the size in units of pixels. And I suggest, because you'll be creating more, this is an iterative process. After orthorectification, I have to do underscore and then the value that I have for my offset. So this is 7. So it created that, and now we will use the ImageJ software. And in this software, once it chooses to pop up, you'll just be shown this. And what we want is to open the image. So we'll do File, Open, navigate to the folder that has the data you're working with. And if you just sort by date, if it's viewed in a different thing, you could just right-click View and go into Details, sort by date, and the most recently made file, the image file, should just float to the top. So now we have this. Let's zoom in. You could hold Control and zoom in and out and guide it with your cursor. And we can now click this button, the straight segment button, and you click here. Let's do it right here. We'll click at one vertex, hold, and drag it to another one. And it will know, okay, that's 114 pixels. This introduces something that I think will be very helpful for honing in on the best altitude offset. And that is in Excel. I have a row and it has altitude offset. Ours is 7, and we have 2 columns, neo and solid. Solid corresponds to a side that only has a solid color along its length, and neo, as in Neapolitan, like the ice cream, is sides that have all the segments included in them. So if we measured 113 pixels for the solid side, we'll just do 113. And by the way, ratio is just the ratio of the two. So I'll just do that divided by that. And let's measure the next side. We'll do this side. And that I can't tell because the window for the picture and ImageJ are 2 totally different entities. So you have to bring them both to the top level, which is kind of annoying, but we have to deal with it. So let's measure the Neapolitan side, 109. We'll go back to here, 109. So now our ratio of squareness is 0.96. I personally like to get it as close to 1 as possible. My arbitrary ratio limit is about 1% of true square. So this just means that we need to modify the altitude offset to be a little more precise. So we can close this image. We can leave the actual ImageJ navigation panel open. But let's go back into SpectralView. And we can X out of this now, and we'll go back into orthorectification. We'll go when it chooses to go. Thank you. So we can What we can do, I didn't really keep track of it, but we could have noted which side was taller. So I think Neapolitan was the vertical side, so it's taller than it is wide. And if we made notes in the past on how changing the altitude offset would affect the squid, like how it's squished, you can more precisely hone in, you can more effectively hone in on the altitude offset. But we'll just do 8 because we were very close last time, so we don't need to change it by a whole lot. Let's make sure that the settings are all correct. I accidentally, I guess, started the process, but I'm going to make sure that things are all correct, which they are. The geoid correction and invert columns are the important ones. The especially important ones, I should say. So let's just create the cube again, open that, and we will once again just go to the picture icon, and we will change that now to 8 because now we're working with a altitude offset of 8, and we will reopen it. You can see since we sorted by date, 8 floats to the top, so we just go select it, zoom in. You can pan with the hand button. That's pretty helpful. And we'll just measure again. So we'll measure the solid side, 110 and 106. So 110 is the solid side, 106 is the Neapolitan, and our offset is 8. And we could just drag the math down. So it didn't actually improve a whole lot, which I think is just because I very roughly measured it. But overall, that's not very important. But what we want to do is over time, just try to get the Neo number and the solid number as close as possible. Had I been measuring with more care, we would have found that 7.5 for this particular image is a really good approximation for the way to go. So that's all we need to, this is the only number that we need to know for this step. And in fact, we don't need to process this right now in this single window. We could save time by just exiting it, go to batch, orthorectification batch, and now we'll add the files. Once again, we could just sort by _RD_RF.HCR. So it only includes files that underwent the radiance processing step and the reflectance processing step. And now these are all reflectance files. We'll import them. Settings, let's just change it to 7.5. Make sure that this is off. Click advanced settings, make sure that these 4 are on, and we can begin processing. However, just because the image is squared, I say in finger quotes, doesn't mean they're aligned. So we can once again save time by only selecting the RGB images when we actually do the alignment process. Under batch, we're going to do something new. Keep the _OR to signify orthorectification, but add .tiff because currently the data is in some proprietary format only used by SpectralView. This is going to allow us to open this in QGIS. Unfortunately, for some reason, for just this step, there's a long delay before ending one file and starting the other. And if you have something like 40 or 50 tiles to process, that's where the step really adds up. But there's always other stuff that you can do in the meantime. Anyway, while we wait for this, let's just open up an instance of QGIS. And we'll go into a new project. And I suggest making a new project for every single field that you're processing and work on them all independently of each other. Only input data from other fields if you want to compare different fields, or maybe the same, like different flight missions over the same field. So what we can do, we could just save this right away, and we can navigate to the field so we can navigate to where we want to be. So training, 3 centimeters, and I like to put it here so it's not mixed in with all of the other files. And I'll just do QGIS, airport, 3 cm, and I'm just going to include training. I'm pretty sure you can't start file names with numbers. So if you want to start with like 5-32, 5-45, you won't be able to. So that's why I just include QGIS in front. And during this time, you can input data that might help you get your bearings, or they might be important in other ways. For example, I'm going to import the BARC fields 2020, and I will include the sampling locations. So we can now just get a reference of where the image is relative to everything else. However, this SOP, and I want to stress this, is made to create a coherent image within, like, for the image tiles. The image won't necessarily lie true on the ground in reality. The idea is to then drag the polygon points, the vector points representing sampling data, to match your imagery, just because that's a lot easier than having your imagery match the sampling points. I think I received a Slack message. If that was a Teams message, I don't know what the sound is, but you could just say something if somebody had a comment. If not, that's totally fine. Okay, so now reflectance is done, and let's see how the images under our first pass lays on the ground. So I'll navigate to my training data here, and unfortunately, you'll always be given the option to import stuff that doesn't actually have GIS value, but you could just find all of the tiles, the files that have the TIFF suffix at the total end, not tiff.hdr. So you just want the .tiffs. And that looks like, I just right-clicked. My bad. Let me reselect these. And let's drag them. So there should be 6 files. I'll collapse them so I can count them easier. You could collapse and expand with these buttons. And we have 6. You'll notice, though, we have these black borders around the maximal extents of each image. And those are not good to have. What you can do to remove them visually, but that data will still be there, is double click, go to transparency. It might start you off at like information. So just click transparency, additional no data value, just put 0. And then you could hit enter to automatically complete the process. So we saw that. And you could just go to every image. It's annoying to do it manually when you have like 40 tiles, but you only have to do this process once, which is great. So now we have the image. At a distance, it's pretty cluttered looking, so we don't have a great sense of alignment. But if we zoom in a bit more, we can get a better sense. And before we look into this more, I suggest that we reorder these tiles. So what QGIS does, and it's pretty annoying, is if there's a number sequence, it will order them based on like the value of the leading number and then going one by one. So even though 7,000 and 9,000 are earlier than 14,000, they'll appear later because 14,000 starts with 1 and 7,000 starts with 4. So they'll be pretty well aligned, except you'll get some outliers. But now all these are numerically aligned, and we want to just group them together into the group, like into the strips that they belong to. So we see 1, 2. So we now know that these two are a strip. You could click one, hold shift, click the other, and push G or group selected. And we'll do that just because we'll do that for the others. And an additional thing that we want to do is create a larger group that contains these existing groups on whether they're an even number group or an odd number group. And I'll get into why soon. So we want to click, hold control, click group 3, so that avoids selecting group 2, and we will once again join them. And just to mirror that, I'm going to create another group of 1, and we will rename these groups into even and odd. And this will be very important soon. So if we take a look, we can see that the alignment is actually pretty good. However, if we toggle on and off, let's put evens on the top for. Sometimes it's better to get another perspective on what, and you can sort of get that by changing the order in which layers are drawn. And we can see that this middle layer seems to be a bit more to the west than it needs to be. And we don't necessarily need to worry about up and down just yet. So let's just worry about one axis of alignment. And we're going to worry about what I'm just going to call the longitudinal axis. And to change the longitudinal axis, we need to adjust the pitch offset. And this very simple diagram shows as you change the offset, it'll move the tile strip in a given way. So pitch will move it along like longitudinally. Roll will move it transverse or latitudinally. And a yaw offset, which I'll get into in a little bit, will rotate the image, I believe, about the center pixel, roughly. And an important thing to note is that these offsets will only affect the tiles on a per tile basis. So if I were to change, so if we see that each strip is composed of 2 individual tiles, if I were to change the yaw offset of both of them, they'll rotate independently of each other. And if I change the roll of one tile, it'll only affect that one tile. So that's why we need to process things generally in groups, just to save us a bit of headache. But let's just begin with orthorectification. And we pointed out that we could move this tile, this even tile strip to the east, which is great. We know we have a mission. Let's try to figure it out. The issue is we don't know if we need a negative or a positive pitch offset. And the only way to figure that out is to experiment. So we see evens are 14 and 16. So we could just go back here and delete everything else because we'll only be working on the even tiles. And this is actually a good time to introduce lists. So when you input, let's say, all the even tiles, if in the future you want to process all of the even tiles, instead of selecting them all manually using the add button, we can import them all in once, click this red down arrow button, and we can navigate to where we want it to be for training. And we can rename it. I like to say batch ortho. And then this is an existing one that I have for odds. This one's going to be evens. So you saw that I had one for odds. If I delete all these tiles and I want to like, I want to add all the even tiles, you just load list, batch ortho evens, and now you have all the even tiles again. And what we are looking at here, so if we look at like a specific feature, like where one tire tread begins and another ends, even though they're not perfect, we want to keep a note, say, okay, these are off. We need to move it west a little bit. If I arbitrarily change the pitch to 1, why not? Leave the roll the same, leave yaw the same, make sure the settings are what you want them to be. Once again, only do RGB. And this time we do need to overwrite these existing files. So we'll do that. While this processes, we need to close, save, and then reopen QGIS after it finishes writing all of the data. And that's because QGIS only pulls the spatial information from the header files when you input data into the program or when you start the QGIS program itself. So only now will it update with the true values. Like I said, the alternative is to re-input the data, and then you have to add the additional no data value of 0, and this is just a much better way. So we've determined, we've changed the we changed the pitch positively from negative 0.35 to 1. I'm going to close this now. That ended up moving it in the wrong direction. And that's important to note. So let's note that right now. What we have to do, evens, roll, pitch, odds, roll, pitch. And I'm just going to say positive equals moves left. And if this is true for the evens, because the drone flew in the other direction during the odd tile strips, it's going to be the opposite. And this is why it was important to group them into evens and odds. So now we have some information. So let's just change this. If we change it to, it moved it quite a lot when we went positive. So when I go negative, instead of changing it like to a high magnitude of difference, I'm going to do negative 0.75, which the number is just sort of partially arbitrary. An important thing to note, and I actually messed up here, when you do to each local file, that just basically says save these settings. So what I actually forgot to do when I adjusted the altitude offset was do save ortho INI to each local folder with the updated altitude offset. So that's not a terrible deal, but what that means is I'm actually just going to take a picture of that, save it here, and I unfortunately do need to reprocess the reflectance data to the correct altitude offset. And like I said, with 6 tiles, that's not a huge deal, but it's just a little bit of an annoyance. And I'm going to once again use the default values, except once again update the altitude offset. Yeah. So yeah, just as a warning, it's very easy to sort of forget to select certain options and update stuff. This software provides you with very little user feedback in terms of what, like how the settings you select will shape processing or shape how the software behaves in the future. So just always just try to stay on the ball on that.
One bit of time saver that I've discovered is that you can measure how far off you are, east or west for your pitch. Figure it out in meters and divide it by the altitude that the drone was flown at and calculate the arc tangent to get it into degrees. And that'll give you how much to adjust your pitch and roll by.
Oh, I didn't actually know that. That's also a good option for sure. Okay, so that's process. Let's reopen this. Well, actually, let's just adjust the even changes. So these are the even row tiles. And we need to, once again, update the values to, with this method, hone in on the true value. So let's do negative 0.75. We'll process these two tiles. In the meantime, we'll close QGIS. And we will wait for it to finish the processing. And we will relaunch QGIS. Okay, so alignment in pitch is pretty good now. Where we seem to be off by the width of a tire tread. That's roughly 30 centimeters, maybe. But given your tolerances, there could be room for improvement. So we can just, once again, change the offset. We were going in the right direction, which is great. So we'll only change it by relatively little compared to what we did before. To save time for this tutorial, I found that this should be a pretty good approximation of correct. But once again, this is an iterative process, and if you don't choose to do the math arctan method, which is probably the better way to go, it's just it just takes a little time to hone in on where you want to be. Okay, so we can see that this seems to be very well aligned with the tire treads of the adjacent row. However, if we look along the length, we can see that perfect alignment is not the best way to put how things are currently, because we could see these duplicated features. And that's because in an area where there is overlap, there is still some misalignment, except in the transverse direction. And we could see that the misalignment is very little. So we'll change the value this time of roll. And because it's so small, we don't have to change it by much. And what you'll do is choose a value arbitrarily. In this case, maybe not too far, but far enough to be able to determine how changing the role affected the final image. And if you want the wrong direction, you just change it the other way. If you overshot it, but you went in the right direction, just lower the magnitude of change. So I'm not going to go through this process just because I did the same thing with pitch already. And we found that 0.2 was pretty good. Something to note. Never mind, actually. Sometimes you'll see that small changes in offset can have variable effects on displacement, not just at like, oh, if you change like a change of 0 degrees to 0.1 degrees is very small on the ground, but a change of 20 degrees to 21 degrees would be more on the ground because you're looking at the ground from the drone's perspective at a more oblique angle. I think that's the right use of oblique, at a more extreme angle. So as you approach the horizon in terms of your degree offset, a small change will lead to a significant difference on the ground. Additionally, the height of the drone will play a big difference. So these values you need to sort of come up with over time on a per mow the lawn per mission basis, because a drone might be flying at different altitudes. So we've processed these to what should be pretty good approximate alignment for both pitch and yaw. Let me just save and save. It's freaking out because for some reason I had 2 projects open at the same time. Yeah, save that. Okay. So we can see okay, so things aren't still perfect. I don't know why. I'm not quite sure exactly why, because I'm using offsets that I thought were correct, but we can just pretend that these are correct, and I'll just check my own data later on. So let's say that everything is aligned, things look pretty good. Obviously, things won't be perfect due to just reality getting in the way. But let's say things are up to standard and we will process, we're ready to process the full data cube. So what we do is let's exit out of QGIS. And let's say that these were the list of offsets that were accurate, or at least like past inspection. For every group that has different offsets, you need to process them individually of each other. So in this case, here, so I'm going to just open up my completed, and I'll just randomly go here. And in this case, we can batch process all of the tiles in groups 1, 4, 5, 6, and 8 in the same cycle. 2 is different. That has to be done on its own, except for 7. These 2 have the same offsets. And then 3 has to be done independently. So overall, we do the processing over 3 cycles, and you can batch process them in these groups. To do that, we'll once again go to ortho rectification. I recommend making this take up one side of the screen and your spreadsheet with the table of offsets on the other. And we can adjust it so it doesn't take up a whole lot of the screen. And we can, let's say, batch process this even set, which has all the same offsets, to the given numbers. Make sure that, once again, this option is disabled. These 4 options are enabled, and that your offsets are correct given your table, which this is of an arbitrary table, so you don't need to really worry about that in this situation. Under wavelength selection, we'll go to select, so it selects all of the bands. And for overall the suffix, I like to just do _OR _ all _ bands. And then you simply process them. And that takes quite a long time, so I will skip doing that. At the end of the day, you will have this folder of each tile, the different processing steps, and then the final step will be similar to, hold on, it'll look like this. So the final step will look like this, except it will be RD, RF, OR, all bands, .tiff, and then a corresponding .tiff.header file. And then from there, you could choose to move them or organize them as you wish. The important thing is you always have to keep the header file associated with the all data file together. So under like in my case, completed data cubes, you could see a random tile, all bands.tiff, and then all bands.tiff.hdr. And then this as a pair is a single tile that's processed to full hyperspectral bands, and that along with all the other bands in the flight mission should create a passively coherent image. And then from there, all you have to do is then line up all of the images, line up all of your sampling locations if you have those files to where they belong on the imagery itself. In this case, this is the same flight, except data that I actually processed to better completion. You can see in the end that there are still some offsets. We can measure the offsets just because they are imperfect. So this is a meter off roughly. So it's not great. There's room for improvement. And your level of improvement is just how much time you can spend with the data. One thing to note is that sometimes, in this case, all these files do render well together. Something that I have noticed, I think it's in this flight collection effort, is that sometimes when you process the data, once you move them into QGIS or ArcGIS Pro, you'll get these really weird rendering errors, and they can manifest themselves in different ways. This is one such case where several tiles are improperly being rendered, and they, in this case, appear as these really weird stripes. And as you zoom in, you'll see that they actually then render correctly, and the distance at which you're required to zoom in for them to render correctly can change depending on the tile. And that's just something to keep in mind. The data should still be there, should still be preserved in the correct form. It's just that for some reason, there's this error that has to do with actually visualizing the data. And that's just something to be cognizant of. Anyway, let me quickly scroll through my SOP, see if I forgot anything. It doesn't seem that I had. So if there are any questions, I'm now done with my training, at least going through the SOP method. If there are any questions about the software or the utilization of ImageJ or QGIS, I'll be happy to answer them. Okay, it doesn't seem like there are any questions. The software is, it can be a bit of a pain to use, and as you do use it, you'll definitely lament. Okay. You'll definitely notice areas where they can make really obvious improvements, where they, in SpectralView, that could vastly simplify this process. But as you process more imagery, you get used to it and you'll get more efficient. Let me see some text that popped up. Okay. Do I have any points? So spectral Headwall. So SpectralView, in my opinion, is not good software, especially when you compare it to more commercial and mainstream software like ArcGIS or even QGIS. So there isn't like you can't really use Stack Overflow or Stack Exchange or any real forums to try to come up with a solution to a problem you might have during processing. The software, this is niche enough that you could go to Headwall's, maybe their knowledge center forums, but you could create a customer support ticket with a problem. And I found, at least in terms of response times and willingness to help, that their staff is really on their game. They'll get back to you very quickly. Let's see. So they're a good resource. Obviously, you don't want to bug them too much. I would highly recommend that you use QGIS over Arc Esri products. So ArcMap, which will, I think ArcMap is going to be no longer updated really or supported, I think, if it hasn't already. So ArcGIS Pro is where you should be going if you do use Esri geospatial software. I would recommend using QGIS over Esri products because the process of me closing QGIS and reopening to update the tiles given their new header information during my iterative process, that doesn't work as well in ArcGIS Pro. I guess they have a different way of calling to data or calling to files. So yeah, use QGIS and just constantly close and reopen. That's the best method. So you only have to create zero, like you only have to do the like double click and then add the no data value and then okay once per tile. And then you just keep those tiles and they'll constantly be updated during your iterations. Let me go to PowerPoint and see if I have any other insights that I maybe haven't really expanded on in this presentation. Always keep invert columns on. That's really important, at least if you use the same drone setup that was used for the data that I collected, that I processed. Just remembering something like this is very important. How these offsets affect how the imagery is changed. It's really important to keep note of how changing your offsets will affect even an odd imagery. So let's just say if a positive pitch offset would move the image down, in this case, in odds, it would move it up. So it would be that. And just keep that here. So in case you ever have to come back to it, this information is right there for you and you don't have to figure it out again. Someone was typing. Let's see what Okay. No longer typing. Anything else? I think the biggest thing really is to be really good with your note taking in terms of like your tables and stuff like this. It'll really help you out in the long run so you don't go crazy having to navigate into header files for individual tiles. I think that's about all. I heard someone's mic go on. If that's someone.
It's me, it's Matt. So back to the classifying your weight reference. So maybe I'm learning something. I have always ever just right clicked and selected a a single pixel, but you're able to actually do I guess you're using an average of all of the weight pixels.
So what I think happens, in this case, this is a bad image to use because it only displays RGB bands. That's why you don't have any information really. What I think happens is you have the original seed pixel, which you right click. From there, it does a rough estimation based on this default SAM limit parameter to try to identify other pixels on the tarp. And then those pixels are then averaged together to create some data product that's used to convert from radiance to reflectance. If that product contains pixels that, in this case, have the white, gray, and even black, in reality, it will be more white and gray. Then you're going to have a reflectance like a scene white reference that's informed by white pixels, which is expected, and gray pixels, which I think is unexpected by the software, because the data that the white reference that it produces is for a specific section of the tarp.
Right.
So I think it is important to hone in on just the white sections of the tarp. And then once again, that's done by drawing the box and then by adjusting the SAM limit to the limit that SpectralView says is at least 500 seed pixels when you recalculate. In an attempt not to be overly, I don't know what the right word is, overly lenient with the SAM limit and then have it do something like this. I try to keep it not far above 500. That way it's really strictly constrained to pixels that look white. Yeah.
Okay. Well, it's good to know. It's good to know. Just some other things that I've picked up along the way, processing is that if you happen to have two data cubes or tiles that have like the reflectance tarp in, that's always a good constant feature to use to adjust your roll and pitch between the two, so you can line up the tarps between the two tiles.
Yes.
One in one direction versus the other direction. And then the offset, figuring out your pitch and roll offsets. That was a big time saver using the arctangent method. It takes out the guesswork a little bit. I mean, you still have to play around with it a little bit depending on how close you want to be, but it gets you close to in the ballpark right off the bat.
Okay, yeah, no, I think that's a good method, and I just didn't know about that. But to expand on that, for my example, I used tire tracks, and in this case, you get in a straight line that goes across. You can match it up, but you don't necessarily know where along the straight line it really belongs to, so you generally need to refer to another feature. Point features are that's where point features really shine. So if you could align like the easternmost extent of a point feature between two images, That's perfect because then you have pitch and roll. Obviously, with my method, you have to navigate by changing the pitch and roll individually. However, once you know how changing them affects the final output, you can modify both of them at once and be able to have a good idea of how that should behave. But yeah, try to find very obvious features, point features, corners of the tarp. If you don't have that option, tire tracks are a good option, and then you can get a sense of alignment by seeing how they change by looking at different tracks that go across the boundary. Going to the question that, I'm sorry, I don't want to butcher your name, Sardorbek had. Is 16 gigs of RAM enough to process? That's really where there was a limit of capability. I originally started with my personal desktop at 16 gigs. I think you can process imagery totally fine with 16 gigs. However, you may not necessarily be able to process as much imagery at a time. So what might be 1 or 2 steps for the laptop that I'm on with 32 gigs might be double that, or it might be a little more. So you can still do the job, I think.
Thank you.
Yeah. For processing, okay, so for processing one field from raw to finished, now that he has practiced, what is an estimate of the time required for data processing? So, okay, so processing up to reflectance is super easy. You could do that in you could do that in 40 minutes. Processing orthorectification, getting the aspect ratio down could be an additional 5 to 10 minutes. Could be an additional 5 minutes. This is where the real problem is with quantifying this effort. If things go well with my methodology and you're fine with having one set of offsets for all even rows and one set of offsets for all odd rows, you could get those offsets down in let's just say an additional hour just to play, an additional 40 minutes to an hour to play it safe. Maybe for every additional tile strip that you need to offset individually, for example, for this, I had, well, let's do a more clear one. For this one, this is an outlier in a row of what's very nice and clean. So let's see, let's say 25 to 30 minutes per offset. You have 2 offsets, that's like an hour. So let's just say if things go well, you can get everything completed in terms of the hard stuff down in a few hours. An additional tile to offset's an additional 30 minutes. To process all of the bands in SpectralView, so if you did batch ortho, and then you went into wavelength selection, you selected all, and then you did OR.all bands, that can take quite a while. That can take, it will be done overnight, but it will take multiple hours. For let's say 40 tiles, let's just say it could take 4 to 5 hours, maybe. So overall, you're looking at maybe a full work, like 3 hours of processing, like of actually doing work, and then additional 4 to 5 hours of processing, during which you could do overnight. Yeah. Let me see if there are any other questions.
This was a lot of excellent material, Eric. Thanks very much. I managed to join on my phone like Matt did, so I got into the Vocosphere after all.
Okay.
Any other
Yeah.
questions from anybody or Matt, since you've had a lot of experience, any other tidbits of information that we should add to this training?
I don't think so. I mean, Eric seems to have got the process down. I mean, that's very similar, aside from a few things that I'd mentioned already. But yeah, no, I think he's covered it.
So just to reiterate, the method that you use to calculate the pitch and roll from the arctangent, would you just restate what that method is?
Yeah, so it's so I use ArcMap or ArcPro, but QGIS is just fine too, where you measure the distance in meters of how far off the two tiles are from one another in roll or pitch, and then you divide that distance off by your altitude that the drone was flown at, which is also in meters.
Which you would pull from the flight plan?
Correct. And then from that, you would then calculate the arctangent to take it from meters into degrees. And then that's the offset that you would apply then to the roll or the pitch.
Got it.
So yeah.
And then do you tend to use like a center track and then match the side ones to that? Or do you tend to do one for all of the odds and one for all the evens?
I tend to have an ortho file for the odds and the evens. It's typically how I've done it. I'll work usually with a lot of our fields. Unfortunately, we don't have like tracks or very defined features. So a lot of times I'm just working with whatever images I have of the reflectance tarp, and making my adjustments that way until the tarps are aligned in the two tiles.
Great. Eric, if you don't mind, do you mind typing in your contact information, your email, I suppose, if people want to get a hold of you with questions? I think that's about it. I think one of our lessons learned is that the next time we go out and sample, that we're going to put 2 visible ground control points, one on either side of the sampling location, offset by a couple of meters, so that then we can very clearly identify the area between the 2 bucket lids, is what we use as the area the sample was collected, and extract that data for comparison with field data. So I think we'll do that moving forward. Okay, wonderful. Eric, thanks so much. Any final comments before we turn the recording on?
No, I think that's about all.
Just want to say nice job, Eric. This is it's a heck of a lot of work getting this imagery all geo-rectified and all, and you did quite a bit in a short amount of time. And thanks for leaving us in good hands with the SOP and your run through here. Appreciate
not
it.
a problem. You're all quite welcome.
Very thorough. Okay, I'll stop recording.